Hello everyone, this is Mrs. Ransling coming here to talk to you about some rules for calculating with significant figures. So when we do work with calculations that have been based on measurements, we have to take into account the significance and precision of those measurements when we report our answers. If we report more digits than what was actually possible from the tools, then we're kind of lying with our calculations. So there are two ways that we end up rounding based on the type of math that we are doing. If we are exclusively adding or subtracting, so there is nothing else happening except for adding and subtracting, we are going to care about the place values of the measurements involved. And since we can't report more than the least precise place value, we're going to use that as a way to cut off or decide where to round our final digit. What you're essentially doing is establishing that estimated final digit. So what would be an example where we would have this kind of a measurement involved in a calculation? You might be doing measurement by displacement. So in this situation, we take the measurement of a volume of an item placed in water, and then we subtract the initial volume of the water without the item in it. That difference between the two would represent the volume of the item itself. So here, when we take a look at our volume of the item in the water, whatever happened, the measurement was reported to 2 decimal places. We see reportment to the hundredths place. But whoever took the measurement of the water without the item only reported to the tenths place, which means that the 1 in this case is estimated. So when we look at our calculation over here, I like to line it up vertically because it gives us kind of this nice way to cut off and identify where we know the whole value versus where we don't. The calculator would tell me that 30.56 minus 24.1 equals 6.46. However, because this is estimated, we don't know if it's 0.14, 0.11, or it could be 0.08 and be rounded to 0.1. So we are going to round so that the final digit of our measurement is in the tenths place. That means we look at the 6, and since this digit is a 6, we will choose to round this digit up to the 5. So the accurate reported measurement for this would be 6.5 milliliters. And I chose to round there because the tenths represents the most measurement I could report based on the least precise place value. I'm going to cut it off based on essentially the least information measurement. And again, we used our rounding rules. The 6 is higher than 5 or higher, so that makes the 4 round up to the 5, as opposed to remaining a 4. Again, this is only when there's exclusively adding or subtracting. To be honest, this is not the most common way that we do calculations in chemistry. A vast majority of our calculations involve some form of multiplying or dividing. If there's multiplying or dividing involved at all, even if it's combined with adding or subtracting, we're going to round at the end of all of the work, and we're going to use a slightly different rule. This time we care about number of significant figures, not the place value, but how many significant figures there are in the measurements. The measurement with the least number of significant figures is what is going to provide us our rule for rounding. So let's say we are calculating an average atomic mass. It's a good example of a calculation that combines multiplying with addition. When we look at our values provided for these isotopes, the first thing we want to consider are how many significant figures are present in the measurements. Both of these have 2 sig figs, because they each have 2 non-zero numbers. Here, this one has a captive 0, which is significant, and 4 total digits, so this measurement has 4 sig figs. This measurement has all non-zero digits, so they're all significant. That means we have 3 sig figs. So when we take a look at our answer, we see that the calculator spits out 41.1878. Now that answer is more information than what we can report. There are 6 significant figures in what this is reporting right now, and that's too many. So what we have to decide here is among these measurements, which are the least precise that determines how many significant figures to round to. Both of these values have only 2 significant figures. That means our answer can only have 2 significant figures. So when we look at the 41, we're going to kind of start counting from the left. That means the 4 and the 1 are the digits we'll keep. And then this is what we have to round and remove because it is more precise than what we're able to report. Since the 1 is less than 5, that means this 1 in the 1's place stays a 1. Our final reported answer would be 41 AMU. Now notice, that means the average atomic mass based on these measurements is equal to the one of the isotope. But it only made up 90.61% abundance of the isotope. It would be much more precise and therefore actually in this case accurate to report more digits. That is why we are going to typically keep more digits when we do our atomic mass data. But in this example, we would be limited to reporting 41 as our answer because we can only report 2 significant figures. What you will see is we're going to do a few more examples within Edpuzzle, and then you'll have a chance to do some practice on a Canvas quiz and get some immediate feedback on if you are accurately determining significant figures in your reported answers.